Brady, we're very happy to have Professor Michael Douglas, who's going to tell us about Calabi-Yam metrics and holomorphic networks.
Yeah, thanks, Yang. Thanks everybody for inviting me to this conference. So I'll describe some work I did with Subramanian Lakshminarayan Sinhan and EDG to graduate students at Stony Brook, and with the early stages to Shabana, who unfortunately passed away, but very promising student that we feel the loss of, but in any case, he it was good to work with him. So, okay, so I'm going to give largely a talk I gave at string data with a review of this whole topic of numerical metrics on Calabi-Yam manifolds, and then our recent results using machine learning techniques. So I imagine, by far most of the audience is familiar with Calabi-Yam manifolds and their basic use in string theory. So it's clearly a very central part of string compactification. And there's this whole class of, both physical and mathematical questions for which we would like to know the Ritchie-flat Kähler metric. Basically, physically, anything that really depends on the Kähler potential, such as normalizations of fields and thus physical Yukawa couplings. We would need to know the metric to compute. And so that has motivated a fairly sizable literature on numerical methods to compute the approximations to the Ritchie-flat metric, starting with Hedrick and Wiseman, who computed an approximate K3 metric. Simon Donaldson proposed a general technique of using embeddings in projective space through sections of a line bubble that I'll go into some detail about. And then this has been, always was an activity in this direction, but revived in the last year or so by Ashmore, Yang, and Bert Overett, that, and then a few more works that have used machine learning inspired techniques. Okay, so here's the quintic, everybody's first example of a Calabi-Yam. And the main virtue of the techniques we'll describe are that you can treat quintics with no symmetry, but this one has the more or less maximal possible discrete symmetry, so that simplifies the discussion. The Calabi-Yam geometry can be used to show that the Ritchie flatness condition is equivalent to the condition that the two natural volume forms, the standard Kähler volume form, and the volume form that you can construct from the holomorphic N form are proportional and with some appropriate normalization equal. And so that's a substantial simplification. And then put it in context, one can, of course, this very large subject of numerical method for PDE. You can break down most methods into local methods, such as finite elements. You develop some sort of a mesh, or you sample, you represent the functions in terms of their values on points, and spectral methods, where you have some sort of a function basis that you expand in. Okay, so again, to make a brief survey of techniques people have tried. So Hedrick and Wiseman basically used a local method with explicit coordinate patches for the K3 that they described. And then if you have an elliptic PDE, relaxation methods tend to work well. But then 6 dimensions or even 4 dimensions is pretty large from the point of view of local methods. As you all know, lattice gauge theory in 4 dimensions, it took many years before the computers were up to that challenge. I mean, a classical PDE is not quite as challenging, but nevertheless, you need number of lattice points, which is basically the power of 1 over the ratio of length scales well, the ratio of length scales in the problem raised to the dimension. So that power-like dependence is makes it grow quickly. Okay, so then Donaldson obviously came from a more mathematical point of view and proposed a embedding method, which was closely akin to the work he was doing at the time on Kähler-Einstein metrics. And so, again, embedding methods are not as popular in the general PDE field, but certainly not unknown. And then in machine learning, the kind of the standard first example of embedding method is what's called the Laplacian eigenmaps, where you say, take a graph and take the graph Laplacian and take the eigenfunctions of that graph Laplacian, and then you regard the set of eigenfunctions as mapping each point of the graph into some Euclidean space. And so this is a nice, very natural embedding. Now, in the context of a manifold, or even for the graph, it's a lot of work to solve that Laplacian and then to vary the solution if you're doing a problem where the metric is actually varying as you find the solution to a PDE. So that's, again, that's one reason why that type of method is perhaps not as popular as others. But of course, in projective complex geometry, there are very natural embeddings. You choose a very ample line bundle, and then the set of its sections gives you an embedding into a projective space. And those, of course, are just given to you in the case of these algebraic varieties, hypersurfaces. So that's a huge advantage. And then you can pull back the Fubini-Studi metrics. So on the original projective space, of course, they're all equivalent under linear redefinition, but once you pull it back, you get a parameterized family of metrics. And as you consider higher and higher degree line bundles with more and more sections, you get a succession, a family of these parameterized family of metrics with more and more parameters. And so that's like a spectral method in the sense that there's this natural functional basis that you can expand the Kähler potential or e to the Kähler potential or the other functions in your problem. But it still has this problem of cursive dimensionality. The number of parameters grows more, the same power law as it would for this local method. Okay, so then you can do the standard, as relaxation or optimization or other methods, but now there's this method which is particularly adapted to Kähler geometry. Although it would be very interesting to ask, how far can you push this beyond Kähler geometry, which is this method of the balanced metric. And so what's a balanced metric? It's a metric, there are conceptual definitions, but I'm just going to give the definition in terms of a formula. We take some basis of sections. We can use it now to define, given a metric on the projective space, we can regard, e to the k as a Hermitian metric on the line bundle, and so we get a natural inner product on the space of sections. And then essentially the balanced metric is the one for which the that inner product that you get from this calculation, you're computing an inner product on M, agrees with the inner product that you've postulated to define the Fubini-Studi metric. So that's what this condition is. And then that's a mathematical condition with a lot of interesting uniqueness and ability to prove when solutions exist. It has some physical resonance. For example, you can say that there's a physical interpretation of Kähler geometry and the holomorphic wave functions as quantum Hall states. And then this will be, in fact, the condition that the density of states for such a quantum Hall system is a constant on the manifold, which again, maybe there's some physics to be had from this paper of Eager, Gary, and Roberts, as well as some work I did with Simeon Klevtsov, tried to find such interpretations. But the mathematical interpretation is, again, the ability to prove the existence or define the obstructions to existence of these balanced metrics is a much easier problem than the actual Ritchie-Flat metric. And as you take the degree to infinity, you can show that the balanced metric actually converges to a Kähler-Einstein metric, or in the case of Calabi-Yau, the Ritchie-Flat metric. So here's a objective function which you could also postulate to, the balanced metric is a critical point of that function. So that's part of the arguments that these exist. Now Donaldson showed that there's a very simple iteration where you just compute this matrix of inner products from the given metric, and then if you take that as defining a next step in the iteration, that will always bring you closer, and in fact will converge on the balanced metric when it exists. And so that's a procedure with an actual exponential convergence. So that's a great advantage of the procedure. The disadvantages of the procedure are that doing all these intervals is kind of expensive, and it doesn't actually converge on the Ritchie-Flat metric, it converges on the balanced metric. But in any case, it works, and Donaldson even demonstrated that it works computationally. And so a number of works went on to use this balanced metric for physical problems, to do it on Calabi-Yaus that were used in more realistic compactifications, to do it for the Hermitian-Yang-Mills equation, and all the way up to these problems of computing Yukawa couplings. So that's an example of the convergence, and this is taking a S2, the obvious rational curve into Fermat-Quintic, and looking at this eta parameter. So we would have a perfect symmetric sphere if eta was constant, and as we increase the degree of the line bundle, you can see visually how that convergence works. But even for k equals 12, you can see it's not a perfect sphere because the balanced metric is not the Ritchie-Flat metric. Okay, so then another technique you could try is to say, well, if we're actually interested in the Ritchie-Flat metric, why don't we minimize some energy function whose minima is the Ritchie-Flat metric? And of course, it's not hard to postulate such functions, starting with the norm of eta minus 1, where you've normalized the holomorphic volume form to get that condition. And so these are also nice functionals. They're also convex. And then in the case where you have a Calabi-Yau with a large discrete symmetry, you can drastically reduce. Although you still have this cursive dimensionality, you can go up to a pretty large K and do the symmetry truncation. And for example, for K3, you can get up to K equals 17 with only 100 parameters respecting the symmetry. And then this is a very good algorithm that can get very close to the Ritchie-Flat metric. Okay, so that's kind of the overview of techniques. And my general take would be to say, if you're just really looking for a Ritchie-Flat metric, then you should optimize the functional that gives you the Ritchie-Flat metric. But if you're interested in more broader questions, such as, do I know whether the solution exists or not, then the balanced metric has many advantages. So the general nature of spectral methods is that approximation error decreases exponentially because we're approximating a smooth function. So it's kind of like similar statement in the Fourier space. So how big a degree do you need? Well, from the point of view of approximation error, you might not need such a big degree, but then there's also the question of what function are you trying to approximate? So there's like the bias and then the local structure of the error, and then you can only represent functions with structure down to some given length scale. And of course, as I commented before, if you don't have symmetries, then all these approximations are going to have a number of coefficients that grow with the power very quickly. So the method still works for problems with no symmetry, but then again the calculations become very large, and these kind of other sources of error become very large. Okay. So does machine learning help with this? And the general expectation would be, well, yeah, machine learning problems, people deal with images with millions of variables and models with billions of parameters. So sure, why not? And so a work that explored this, initially, Ashmore, Young, Hagbert, Overett, developed a machine learning improvement on Donaldson's algorithm, and studied this for Mach Quinte. So this is some general comments about machine learning, which I'll leave in the slides, but not dwell on, and move to our work, which is to replace this most general ansatz for a Kähler potential of a given degree as we'll replace that general ansatz with the output of a feed-forward network. And so feed-forward network would be a succession of linear maps and nonlinear maps, and then iterate, and the linear map at the next layer, nonlinear map, ... Okay, so very, very general paradigm. We can increase, we choose the dimensions of the intermediate layers, and so we can control the number of parameters of the model, in great detail. And so what type of network can we use that will actually be useful for approximating these functions? And now it's nice to maintain the geometry and the complex nature of the problem. And so we like the ansatz that gives us a Kähler potential to have the standard properties of a Kähler potential. So one way to do that would be to say, let's use our network to produce holomorphic sections. So we'll send in as an input a basis of low degree holomorphic sections, say just the homogeneous coordinates. We'll take linear combinations of those, and then we'll do some homogeneous holomorphic activation function, of which the natural choice would be take z to z squared. So each of these linear combinations, each of these degree 1 sections, we could then square to get a degree 2 section. Then we take linear combinations, square each of those to get degree 4 sections. And so we keep doing this, and it goes very rapidly. We get to an exponentially large degree. And now we take the subspace of sections that we obtain by some set of these networks, and use that to produce a Kähler potential. And so you might call this a holomorphic network, because the network has preserved holomorphy at each step. And that makes a lot of sense, but it actually doesn't work so well. And the basic reason, if you think about it and explain it on a paper, is that you need, even for very simple non-degenerate metrics on the Fubini steady space, you would need at least a component for every section. And so, and this doesn't naturally, the prescription I just gave doesn't naturally give you, it constructs each section individually, and then you would need an exponential number of them. And that's not what we want. But that problem can be solved by the slight modification of, instead of putting in holomorphic functions, we're going to put in bihomogeneous combinations of a holomorphic and anti-holomorphic. So we might take, for example, the homogeneous coordinates times their complex conjugates, and then there would be 25 real variables. And we'll still take the activation function to be z goes to z squared. And so something of bihomogeneity 1, 1 would turn into 2, 2, 4, 4, eventually 2 to the L, 2 to the L. And then by itself, such a bihomogeneous function is a candidate. And again, you would make contact with other definitions by taking its logarithm as a Kähler potential. So that's what we mostly worked with once we established that the other description was not as good. Okay, so we could talk about a space, or it's really not, it's not linear subspace, but it's a a space of Kähler potentials that can be realized by a bihomogeneous network with specified layer widths at each layer. And then you can see the number of real parameters. And of course, again, it's completely controllable in the number of parameters. The degree k grows exponentially into depth, but the number of parameters, of course, only grows as a power of the depth. So it's very natural to get models with many fewer parameters, polynomial instead of exponential. So from a practical point of view, a great advantage of this is that this is very close to a standard supervised learning problem. And so really you can implement it in, we do use TensorFlow, Keras, but any of the standard machine learning packages with relatively little work. So here's a very, very brief review of supervised learning. And basically we're trying to interpolate or extrapolate a function with input values X, output values Y, and we're going to choose the ways to minimize some loss, like the mean squared error of the function evaluated at some set of points. Okay, so how does that relate to our problem? Well, we can reduce the problem to interpolation through points by sampling points in the manifold. And in fact, that was what almost all of the previous works did, because that's by far the easiest way to treat a manifold defined by a system of equations. And then we posed the Ricci-flatness problem as the equality of a the squared holomorphic volume form with the standard Kähler volume form. So because we know the holomorphic volume form, we can just compute that from the start. It depended on the defining function for a hypersurface, but not the metric. So that's something we can compute for every point from the start. And so we're really trying to interpolate. We're trying to choose weights that take this slightly complicated nonlinear expression for the Kähler volume form and then use it to fit the holomorphic volume form. And so that really is another interpolation problem, just like supervised learning. And so we have an explicit code, which is on GitHub that you can play with, and it defines a variety of Kähler potential, feed-forward networks of the sort that I described that produce Kähler potentials and can be trained. Okay, so for the rest of the talk, it's not going to be math or geometry. It's going to really be the machine learning aspects of that problem. And if you follow like the paradigm of machine learning research, what are the questions that you would try to ask and answer? And again, they're kind of different questions than the ultimate, physical or geometric questions that we might be, eventually interested in. But from the point of view of getting a good method, which is efficient, one should look at these questions. And then it actually does make contact with some of the current research in machine learning that you can compare with. So here I've listed a few of these things. And obviously there's, detailed questions about the implementation. You always have to choose hyperparameters and optimize these, the architect, the width and depth of the network, the way that you optimize. The questions that machine learning in the supervised learning are trying to come to grips with are questions like overparameterization. I'll describe that. And then really the question I mentioned several times in the talk, can we actually really solve this recursive dimensionality, and instead of having a number of parameters that grows, as just high power of the degree, can we really, because in fact, in terms of the degree, this is giving us a power to log, because again, the degree goes as the 2 to the number of layers. So that's a drastic reduction of the number of parameters. And can we really solve the same problems like that? Or are we just kind of fooling ourselves, and we still need, for a given problem, we need roughly the same number of parameters? Okay, so let me not dwell on the implementation details for this talk, but it's there. A slightly more conceptual question, which always comes up, is if you're trying to solve your problem by minimization, by some sort of a gradient descent, is your function convex, or does it have, is it non-convex, but at least, with, good minima, flat directions, or does it have lots of bad minima? And pretty much, once you get into these nonlinear neural networks, they're almost never really convex. But in practice, you can often find that for a variety of reasons that have been described in the machine learning literature, they're close enough to being convex. And the more and more parameters you have, the better the optimization problem is. That this does not turn out to be a big problem in practice. I mean, obviously it sometimes is, but this is one of the better understood points in the practice of machine learning. And this is the first point where this question of overparameterization comes in, because what you need to compare is how many, not just how many parameters does the model have, but how many points do you evaluate it at, and how many conditions does the minimization put. And obviously, once you get the variational equation for a critical point, you get a set of conditions for each point. The total number of conditions is going to be proportional to the number of points. And so in some intuitive sense, if the number of parameters is greater than the number of data points, you don't have enough equations to pick out a unique minimum, and the model is then over-parameterized, and the energy function can't be convex, although it could be that it just has flat directions. Okay, so let's now describe the problems that we actually studied in our exploration and some results. So again, I think compared to the previous works, the most evident advantage of doing this is that you can deal with scalar potentials with lots and lots of parameters. And so you don't need to make these symmetry assumptions, which is, good from the physics point of view. It's good for studying problems like, we think about finding an explicit SYZ fibration by tori. And then the simplest examples of that are calabi-Yau that have much less symmetry, if any symmetry. And so it's good to be able to get accurate results on calabi-Yau with no symmetry. And so we considered 3 sets, one with an intermediate amount of symmetry. So we've added a function that depends on 2 of the variables, and one that generically has no symmetry. If you took a generic complex value as alpha, it would have really no discrete symmetry. Okay, so this is again the kind of detailed kind of initial work that you might need to do if you were developing such a method. And again, I don't want to dwell on it in this talk, but if you look at the paper, there's a variety of choices that one should explore to see, do they actually improve the results? Are they worth the trouble? So which actual definition of error do you use? Are you overfitting? So you test the error after you train on an independent testing set of points. And sometimes, you can cook up your algorithm to get very, very small error on the the point set that you enforce the equations on the training set. But then if you take some other points, you find that you're just fooling yourself, that the actual error of the model is much larger. And that's overfitting in the statistical sense. We're not doing statistics, but interpolation, you can still have overfitting. Questions like, should we use 64-bit coefficients or 32-bit coefficients? How long does it take to converge? So all the kind of practical details of getting a method like this to work. This is an example of how the accuracy depends with the number of steps you take of the gradient descent for various models. And there's these kind of interesting step-like structures that you often see in these training and are identified in the standard machine learning literature with a succession of leading eigenvalues of the Hessian, and so telling you something about the optimization landscape. But again, the most kind of simple use of these graphs is just to see, have you converged? Maybe you should switch to another optimization method to converge better. That sort of thing. Okay. So we got our method tuned, and then we wanted to make a statement about, well, how accurate is it, and how does this accuracy depend on the geometry of the Calabi-Yau and the parameters such as k, effectively the depth of the network. And And so the two variables that we try to interpret our results in terms of are the shortest length scale of the Calabi-Yau. As you introduce a shorter and shorter scale in this Ritchie flat metric, you expect to need more parameters, or at least this is the case where you have a bigger ratio of length scales, and so you would need to use the ability of the network to represent to have this exponentially large k and represent larger ratios of scales. And then a slightly vaguer concept of lack of symmetry, or we could use the word complexity, that the metric does require more parameters to describe. And so we varied both of those parameters of the Calabi-Yau. And then you can ask a question like, well, now, does the accuracy depend more on the depth of the network, and so the degree of the Kähler potentially representing, or perhaps it depends more on the actual total number of parameters of your model? And of course, these are not independent variables, but you can try to separate these. Okay, so to make more quantitative this question of what's the shortest length scale, well, the way that you can understand you get a controlled shortest length scale is by going towards a singularity, and of course the generic singularity is an ODP, or a conival type singularity in physics language. And so the distance to the singularity in some natural measure would be a good proxy that you could use to work out the size of a vanishing cycle and the ratio of scales. Now, of course, the actual metric, the Petersen metric on the moduli space is extremely difficult to compute, but there is this nice proxy which becomes good as you get closer to the singularity, which is a sort of a natural, basically the distance in the Fubini-Studi metric on the C126, CP125, the space in which the moduli space sits. We have this explicit description of the moduli space in terms of the coefficients of the defining polynomial. And then I actually got the idea for looking at other works on complexity and numerical analysis, that this question of what's the distance to the discriminant locus often controls the accuracy and the convergence rate of numerical methods. And so this is adapted from Bloom et al.'s definition for similar problems of that distance to the discriminant locus. And you can show it, it is some approximation, or it has a definite relation to the distance to a conival point if you're sufficiently close. Okay, so this is the example of the Dwork quintic and this psi variable on the x-axis and the proxy distance that I've described. And this has the interesting feature that that's the conival point, but then as you go around the sphere to the other side, you find that there's a second minimum, which was noticed in previous work, but not for this parameter, for the accuracy, okay, by Cui and Gray. And so you see that, well, indeed, there should be another point on the other side where the accuracy is less, just from this geometric point of view. Okay, this is the more complicated F1 and F2 I described, and this is a kind of a heat map. We're varying both the psi and the second parameter, and now this is a two-dimensional slice of the moduli space, and then the blue region, this is this distance metric, so the blue is closer to the singular locus. And so you can see both that we do have a selection of more singular Calabi-Yaus, and especially for this F2 with no symmetry, the structure of the moduli space and the distance from these slices to the discriminant locus is a rather complicated function. So that's some evidence that that is indeed a complicated Calabi-Yau. Okay, so now let me show the kind of result that, tabulation results. So we run our algorithm with a variety of networks, say 2 layers, 3 layers, 4 layers. That's what these 50, 70, and 300s are. The notations 2, 3, 4 are not layers. Those are comparing with the actual full space of Fubini-Studi metrics of that degree. And then that, again, since the number of parameters grows as a high power of the degree, there's a limit to how far you can push that, but there's this nice observation that we followed in Hedrick and Nassar, which is that you not only expect the error to improve exponentially, but in practice, if you have the error for a series of degrees, you can predict, that you can fit this exponential dependence and predict what is likely to be, what is a reasonable estimate for the accuracy for the best Fubini-Study metric of any degree. And so by doing that extrapolation, we get numbers like this S8, the extrapolation of Fubini-Study 2, 3, 4 degree metrics to the predicted accuracy for the degree 8 metric. And then this is the F1 Calabi-Yau. And you can see that the best networks we have, these these 4-layer networks with both either 70 width or 300 width can both do a reasonable job of getting to the same. So these are degree 8. I guess by my previous definitions, 3 layers. This last layer, doesn't count. So 2 to the 3. So these are also degree 8 Kähler potentials. It's a subspace of the degree 8 Kähler potentials, and they get a very comparable accuracy to the best you can do with degree 8. Okay, here is F2, and it's a more interesting story. So here again is that those pink dots are the best you can do estimated with the degree 8 metric. And you can see that this network with a width 300 does a very comparable job. The network with a width 70, if you're sufficiently far from the discriminant locus, distance like 0.15, then it can do also as well. But as you get closer to the discriminant locus, it does not do as well. It does sort of intermediate between degree 4 and degree 8. And so now we see a separate dependence because these two networks, the purple and the green dots, are both degree 8 metrics, but they have a number of parameters that differs by a factor of, I guess, 1,000. So now we have disentangled to some extent the dependence on degree and number of parameters, and we see this slightly more complicated story. It actually depends on the other structure, and at the very least this distance or ratio of length scales in the Calabi-Yau. Okay, so it is the case that we group these various models first by the degree of the metric. So K is indeed the dominant thing that controls the accuracy. Clearly, there is a dependence on how close you are to the discriminant locus. Your accuracy goes down systematically for all these approximations. And now here's the comparison that I just pointed out. So this 70-70 metric only has about 11,000 parameters. The 300 width network has 187,000 parameters, and the Fubini-Study metric has only 245,000 parameters. So that second network has fewer, but not that many fewer parameters than the full set. And it does seem that you needed that to solve the problem for these more singular Calabi-Yaus to the same accuracy. So here's some evidence that it's not just controlled by K. The number of parameters is important because the any of these networks would be able to produce structure on the length scale 1/8, length scale appropriate to degree 8. And so naively you would say, well, isn't that good enough to do as well as the Fubini-Study metric? But no, for F1, it does seem like it's good enough. But for this complicated F2, it's not good enough. And you do seem to need lots of parameters to get the optimal accuracy. Okay, so from the practical point of view, the upshot is that we can get a mean squared error like 10 to the -5, 10 to the -6 very reliably. So like better than 1% absolute error in this eta, which it seems like a pretty good. It's quite a lot better than the previous work, and probably quite good enough for an actual numerical use of these methods. Here's a few comments about special Lagrangians and how one might try to study it. Let me close by just making a couple of comments about these questions that relate to theory of machine learning, and then I'll stop for questions. So this is trying to make more precise the question that I was concluded the experimental section with of, is it the number of parameters, or is it the depth, or what combination of those control the accuracy? And again, people are studying theory of solving PDEs and approximation. I did not find a clear answer to this kind of question. I mean, people in practice are much, what there's more interested in is functions that are not smooth. But if you have a smooth function, this can be the controlling thing. And my further thinking after, writing the paper before is that it really has to be dependent on the number of parameters. This is not some sort of a magic bullet that can represent even Ritchie-flat metrics. It certainly cannot represent arbitrary functions to the accuracy of the general approximation at that degree. But I don't think the Ritchie-flat metric has some special property that would make the networks better. But again, it's an interesting open question to understand. This is this question about overparameterization and fitting. And so there's another, again, if you look at the previous literature, what you'll find, including in my papers, is to say, well, of course, you got to use many more data points than the number of parameters. We have this Calabi-Yau symmetry. We're going to have to learn 100 parameters. So let's use 50,000 data points. But obviously, if your model has to have 100,000 parameters, then having to use 10 million data points would be a huge, huge cost. And the calculations that I presented before did not use that. They used a number, for these bigger models, they used a number of points comparable to the number of parameters. So now you're leaving this regime of classical interpolation theory and statistics, and it's what's called this overparameterized regime. And although classical arguments would tell you don't go there, machine learning often goes there, and the computations do work much better than some statistical analysis based on traditional statistical ideas. And an example of at least demonstrating that there is an analogy in our problem. So a classic paper of theory of machine learning is this work of Zhang et al. That I cite, where you say, take an image classification model, I think they took CFAR10, and just scramble all the labels, shuffle them at random. Okay, and now according to classical theory, the model should not be able to learn that, because the way the model learns is it has sort of prior, that it's good at learning images, and it can learn correctly labeled images and should be bad at learning randomly labeled images, and that expresses the fact that it's got this prior. But in actual fact, the good models for CFAR10 can perfectly learn that scrambled classification. Of course, they don't then learn to classify anything else. They don't generalize, but it directly contradicts this standard law of statistics. And so we can do the same kind of thing to see that at least we're talking about the same type of problem here. Suppose you scramble the values of the holomorphic volume form that you're trying to fit. And now you ask, can your model actually learn the Kähler potential that fits those? And of course, the answer is if you have fewer points than parameters, you can learn it. If you have more points than parameters, you don't expect to be able to learn it. And there's this nice sigmoidal crossover that shows you, again, I think just that this is within the general class of models comparable to what people study in the theory of machine learning. But for this question, again, you'd like to know, well, how many points do I actually need? What is the argument that tells me that I need a number of points comparable to the number of parameters and not say 10 times that, or 10, maybe 10 times fewer than that. So that would be another quasi-theoretical question that would be very good to get a handle on. Okay, so that summarizes, and that's the end of my talk. So I'll stop for questions.
Thank you very much, Mike, and especially for the concluding talk to this conference. And thank you for the summary and the outlook. So, any questions from anyone?
Can I ask a question?
Please.
Yeah, of course.
Hey, Mike, first of all, thanks a lot for the talk.
Sure.
Second of all, I want to ask the questions. You briefly mentioned both of them, but it was a bit too quick for me to see this. So the first question is, so neural networks are universal approximators if and only if the activation function is non-polynomial. So now, of course, it shows z squared, but you can get away with that because you know that
we're trying to approximate a polynomial, basically.
Exactly. Because you know that in the limit of k goes to infinity, you can get the Ritchie flat metric, at least.
Yeah, that's right. I mean, there's this problem of approximating using a finite degree, Fubini-Studi, type metric, was well understood, and we can think of it as approximating that finite degree metric. So we're approximating a polynomial with a polynomial.
Yeah, good. And the second question. So the plot you were just showing in the end, where you had this transition from, exactly. So I was trying to read this. The test error is constant essentially, and the train error shows this.
Yeah, that's right. That's right. So you're overfitting for these fits with few points because again, you've randomly shuffled the things that fit. So you do not expect any generalization. In this case, that means testing error.
And what was the number of points?
Well, this is a model with, I believe, about 5,000. So k equals 4. Fubini-Studi. This is not a network. This is actually the Fubini-Studi, metrics, and it's just property more of optimization, in loss functions than it is of networks. And so you can work it out, but it's somewhere around this number of 4,000, 5,000 parameters for the k equals 4 Fubini-Studi metric.
Okay, thank you very much.
Can I ask a question as well?
Yeah, of course.
So I also had similar question as Fabian on this polynomial activation function. Actually, there is also my collaborator in the audience, Ting, and I have been trying to get around with this polynomial activation function, still trying to approximate underlying polynomial.
Okay.
We find that because of the neural network structure, if you have polynomial activation function, you still cannot get all the monomials. If you write down the full structure, you cannot get all the monomials. So you cannot.
Well, you can certainly span the space. I mean, it's true that the individual basis elements might not be monomials, but you can span the space generated by them.
If your underlying ground truth function is precisely a polynomial, no noise or anything,
right?
Say a dense polynomial of degree 4,
right?
And then if you use some activation function z2, if you have 3 layers,
right?
Z square, sorry. So if you have 3 layers, then because of the structure of this neural network, you will basically eventually not have many of the monomials.
So 3 layers means applying the Z squared twice. So you do get degree 4, and you're asking, is there no sufficiently wide network? Even as the network becomes arbitrarily wide, are there monomials that you cannot approximate?
Yes.
And if the coefficients are general numbers, with pluses and minuses in my case, then no, you can approximate anything. It's just a big linear space. You have to send me if you think you have a counter example. Email it to me, and we can.
Okay, we'll take it offline. Thanks
Okay.
so much.
Yeah.
Thanks.